go.
Okay,
We're on.
Welcome to episode 2 of the Cosmic Pie podcast. We're live streaming from the campus of the University of North Dakota here in Grand Forks, North Dakota. I'm your host, Wayne Barkhouse, and I'm here with...
Robert Moore. Nice to meet all of you.
Okay, Robert, we're got a slightly different format, as viewers could see from last time. You want to explain some of the changes that we...
Absolutely. So that we don't feel and look all crammed together, we put 2 cameras in now, so that's kind of obvious. But we are still in the same room. So with that in mind, if I happen to glance this way, I'm looking over here at Wayne, and if he glances towards me, it'll look like he's looking off camera. But that's why we're actually looking at each other as opposed to looking off into space or at something else. So just to get that out of the way, we also hopefully have a better mic setup going on. So you'll be able to hear us a little bit or not sound like we're in the tin can. If that's still a problem, we'll work on it. Sorry.
Okay, so before we really get into things today, I just want to also mention that the opinions expressed by Robert and I are our personal opinions and not necessarily those opinions of the University of North Dakota, nor the College of Arts and Sciences, or the Department of Physics and Astrophysics. And we want to thank all 3 identities for allowing us to do this podcast. So let's start off. Robert, did you notice how cold it was this morning?
I don't know exactly how cold it was, but I think it was something around minus 14 Fahrenheit. So it was cold. I mean, it gets that cold, it's just freaking cold.
And you want to know how it makes you feel like it's even colder? Giving that temperature in Celsius, it was about minus 25 this morning when I woke up. Now, if you compare that to temperature, let's say, on Mars, one would expect, well, Mars has got to be a lot colder than Grand Forks, North Dakota. So the actual temperature on Mars, as reported by the Perseverance rover, was minus 20 degrees Celsius today. So it was actually warmer on Mars, at least at that location, compared to the morning temperature here in Grand Forks. Which is something interesting to think about. But of course, would you rather be on Mars standing in your winter jacket, Robert, or would you rather be here in Grand Forks?
I'd rather be here in Grand Forks, just the same. It might be a little warmer, but the air's a little thinner on Mars. It's also predominantly CO2, which would poison me. Yeah, just all the way around, I think I'll stay here on Earth.
So temperature's not everything. Is that what you're telling us?
That's what I'm telling you. Temperature isn't everything. You might think so when you step outside and your nose hairs freeze, but and yes, that's a thing.
But still, I mean, yeah, here on the campus of the University of North Dakota, it really is a beautiful place. And if you're interested in experiencing the seasons, if you happen to live in an area which doesn't have seasons, like in Hawaii maybe or in southern Florida, this is a great place to come in the summertime. The weather around here is beautiful, and so if you're interested, if you're in high school and you're interested in going off to college at some point and like to get an education in the STEM or STEAM field even, this is a great place to come. So I encourage you to don't skip over to University of North Dakota. Please look at us in detail, and we got a lot of exciting things going on here on campus and elsewhere. And if you need further information about that, of course, you're welcome to contact us anytime.
Right. I was about to say that too. Feel free. I welcome emails saying, hey, what's this like? We're keen. We're good to go. We'll get you an answer.
And the other thing too is we do have a live chat that's running today. So if you have any questions for us, please don't hesitate to put a question in the live chat. And if it's appropriate, we will answer it. Can't guarantee we'll answer everything because you don't know the type of questions you get, obviously.
Right.
Now, speaking about location, Robert, let's say that you went up to the attic of your house this evening and you find this lantern.
Okay.
And you decide, this is interesting. Let me wipe that lantern off and maybe I'll put it on display in my living room. So you rub the lantern, out pops a genie.
All right.
And the genie says you have 3 wishes. Now, the first thing you have to realize, you don't want to wish for $1 million because you know what happens then, right?
Then the government shows up and taxes you for half of it and wonders where you got it.
No, you wake up the next day, you look out in your front yard, and here's 1 million male deer running around on your front lawn.
Oh, right.
You never saw that commercial?
I have.
The other thing you don't want to do is, if you have a choice, is to wish that you were at the location of the very center of our galaxy, the Milky Way. Now, Robert, why wouldn't you want to go to the very heart of our galaxy?
Because there's this nice thing called a supermassive black hole there that even if you weren't pulled in, you're probably being irradiated by the X-rays from its accretion disk and other things like that. So, in general, it's an inhospitable environment. Even the radiation from the bunches, the just cluster of stars that's right there would be a problem.
So, Robert, you want to explain a little bit more? I'll put you on the spot here.
Oh, okay.
You like that, right?
Sometimes.
What is a black hole?
What is a black hole? A black hole, as my understanding goes, you may be better at this, but my understanding is it's a place where density is increased to the point that the gravitational curvature, see general relativity, of space-time there has exceeded the limit where light can't even escape from it. So, as I understand, it is a matter of density being the focus and the main point, because it does have to be a certain amount of mass and a certain volume. And that volume where that occurs is called the Schwarzschild radius. And that's what most people think of as the black hole, because that's that limit where light can't get away from it anymore.
Okay, so if we're going to be really technical for those of you who are in the know, then the Schwarzschild radius describes a black hole that doesn't rotate and doesn't have an electric charge.
Right.
In some sense, it's the simplest type of black hole you can think of. But if I were to ask you what happens at the very center of a black hole, what would you say?
I don't know. I mean, we call it a singularity because all the math gets divided by zero there.
So your answer is, I don't know.
No.
That is the answer. Congratulations. We will clap for you. In fact, nobody knows.
Right.
And here's the problem with that. The problem is you're dealing with a lot of mass that's squeezed down into a very small volume of space. Now, we know how things operate when we look at very tiny things. In fact, we have rules of nature, if you like, called quantum mechanics that deals with the very small. But when you're looking at the center of a black hole and trying to understand what happens at that location, the question always ultimately comes up, do you use quantum mechanics because you're dealing with very small volume? Or because the black hole has a lot of mass, and sometimes these black holes have billions and billions of times the mass of our sun, all collapsed down to that very small volume or single point in the center. Because you're dealing with such a large amount of mass, shouldn't we use our theory of gravity to try to understand what's going on in that center? And the modern form of that would be Einstein's general theory of relativity. Now, when you apply quantum mechanics to understand the properties of the center of a black hole, and you get some numbers, let's say, do the calculation, do the math.
Do the math.
As we say. Now use general theory of relativity and do the math. Now, if I were to give you a question on a math test, and let's say, we'll keep it very simple for Robert, for us to even know. 2 plus 2, what would you say the answer is?
I'm going to say 4.
Good guess, Robert. I'm sure you've calculated, so it really wasn't a guess, right? Now, if I gave another student the same question, what's 2 plus 2, and they said 4, you would say, yes, that's right. But what happens if they say it's 10 or some other number that's not 4? Then there's a problem somewhere.
Right.
The problem here is the answer we get from general relativity is not the same as what we get from quantum mechanics.
Right.
So we're left in this conundrum. Do we go with quantum mechanics and use that number, or do we go with general relativity?
Or I'll present the third option. Are both wrong.
Are both wrong. And you can't have two different answers describing the same thing. We live in one universe. It's not two different universes. So that's kind of the status where we're at today, is we don't know what happens in the very heart of a black hole. In some sense, we need to come up with a new understanding of nature, something that marries, if you like, general relativity that describes large macroscopic objects, and quantum mechanics, which describes the small objects. Put those together in some form of quantum gravity as sort of the, some fancy terms that we use. But right now, we don't have a great idea what the quantum gravity would look like. And people have tried this. In fact, in some sense, Einstein, for several decades before he died in 1955, tried to unite the different, forces, fundamental forces in nature, like electricity and magnetism and gravity. He didn't have a great understanding of the strong and weak nuclear forces. A lot of stuff was developed at the time that Einstein was pretty old, and he didn't follow, very closely what was going on in the last several years of his life. And of course, we've learned a lot more since the time of Einstein's passing. And so physicists, scientists have continued this exercise today, trying to unite all of the forces of nature into one grand theory that we call the theory of everything. And of course, also known as the TOE idea.
The
and
toe? I've not heard
theory
that
of
expression.
everything, yeah. TOE.
Oh, theory of everything.
It sounds a little weird when you say, "Oh, I'm studying the toe," and they say, "Is it the big toe or the little toe?"
I was going to comment that it's appropriate simply because, what we're doing right now, at least, is stubbing our toe.
Well, that reminds me of this joke, Robert, that I heard. The joke goes, "I recently heard that the universe is expanding." Okay. But I had this really fundamental question then once I heard that isn't it time to loosen the asteroid belt? Now, when you think about it at first, okay, that's pretty funny, but when I first heard that, I was pretty young, so I actually had to think about it all night before I got it. Then it finally dawned on me.
Right.
Do you have any bad jokes?
Oh, I've got plenty, but, staying on topic right now, my favorite is still, Orion got a new belt, but he didn't really care for it. He only gave it 3 stars.
Oh.
Yeah.
Yeah. So if you know the constellations, Orion's belt, which you can actually see, it's a beautiful wintertime constellation. As soon as it gets dark, look towards the south and you can see Orion in the sky, assuming you're in the right location on the Earth, of course, to see it.
I've met very few people who honestly cannot pick out the belt of Orion in the sky. It's distinctive enough, and most people are familiar enough with the concept. Unlike the North Star, which, somewhere along the line, people got the idea that it's the brightest star in the sky, and they're looking for this big, bright star, and it's just this dim little star. It just happens to sit, it's the brightest one sitting near the pole. But that's another topic for another day.
Yeah, well, just to kind of conclude that, Robert, what is the brightest star we see in the sky?
Northern Hemisphere, that would be actually over the whole globe. That would be Sirius.
Think a little bit more closely, Robert. It was a trick question.
It was a trick question.
Yes,
I fell for it.
You
it's
did.
the sun.
The sun. The sun is by far the brightest star in the sky. In some sense, when you're a young child, you think when you look up at the sun in the daytime, you see how big it is, how bright it is, and you feel the warmth coming from it most times. And then you look at the stars at night, and it seems so cold, so distant, so faint. And you make that connection eventually, whether somebody tells you that information or you read it or whatever the case may be, that if you took our sun and you moved it very far away, it would just look like one of the other numerous stars in the nighttime sky. And so the only reason why the sun looks completely different than the stars at night is that it is so much more closer. It's a distance effect, which is kind of interesting. So getting back to the black hole type of situation, we want to understand what happens at the very heart of the black hole. That's why we call it singularity. In fact, you may know that term that's used in mathematics a lot. When things blow up, go to infinity, depending on the context, we would refer to that as a singularity. And that's essentially what's happening here. You imagine squeezing mass into an ever smaller volume as a black hole collapses. And by the way, Robert, do you know how small the Earth has to be in order for it to actually turn into a black hole?
I used to know this, and if I'm not mistaken, I think it's somewhere around the size of an atom, isn't it?
Actually, a little bigger than that. It's about the size of a sugar cube, and nowadays people would say, "What's a sugar cube?"
True,
right?
But you can still buy those because I have some at home.
They're not as popular as they once were, but now we could say it's about the size of a blueberry.
Right. Okay.
I think most people know what a blueberry is, and so it's about the size of a blueberry. The thing about the Earth is we don't have to worry about it turning into a black hole because there is no known force in nature that would take the Earth as it is and squeeze it down to such a small volume.
Right.
But if you think of an object then collapsing into an ever smaller volume, the size of a blueberry, the size of a tiny ball bearing, getting smaller and smaller and smaller and smaller, just think of one fundamental property. That's all, to keep it very simple, the density of the object.
Right.
Okay? So the classic definition of density is you just have mass divided by the volume it occupies. And so if the volume gets smaller and smaller and smaller and smaller, and yet the mass doesn't change, clearly the density is getting larger and larger and larger. Eventually that volume, as far as we know, now there may be some unknown law or rule in physics that prevents this from happening, but as far as we know, that volume will then collapse down till it gets to 0 in size. Okay? Right. So if you follow the change in the density, as the volume goes to 0, the density does something weird. And you don't need to take our word for it. Just take any number at all. Take the number 5. Okay? Go to your calculator. Okay? Take 5, divide it by 0. What do you get as an answer?
Probably undefined from most calculators.
Yeah, that smoke comes from the calculator. It doesn't like to do that because it's infinity is the answer. So the thing is, when a black hole forms and all of the mass that makes up that black hole that occupies a volume which goes to 0, the density goes to infinity. How can you have an infinite density of anything? You can't. It's a foolish type of situation or number.
Right. It's incomprehensible.
Yeah, right. It's nonsensical.
Yeah.
Right? Unless, of course, it was my bank account. If I had an infinite amount of money in there.
Well, that would be nice.
But getting back to the black holes. So things break down at the center of a black hole into singularity. So we have a lot of work to do about black holes. Now, there's one way around this issue, and that is something that several scientists have taken in the past. Not in so much the recent past, but in a few decades ago. And that was that black holes don't exist. Something happens, Mother Nature prevents us to get into this sort of situation where we have to worry about density going to infinity as volume goes to 0 and all of these sort of situations. Something prevents that. Some unknown force of nature, some unspoken rule that's out there that we don't quite know about, something that we're missing, something's incomplete in our understanding of the fundamental laws of physics. And therefore, if black holes don't form, we never get to that point where we have volume approaching 0, that density goes to infinity. We never worry about all of that. And so you'd say, well, what's the evidence for black holes? Now, Robert, You already said black holes do not emit light.
Right.
Okay? In fact, you can think about it, you'd have to travel faster than the speed of light to get away from a black hole. And from the point of view of general relativity, when we're talking about fancy things like curved space-time and all that, space curves in on itself when you're within a certain distance of the center of a black hole. So even if you're a beam of light, all you do, you can think of it this way, you have a path, but that path doesn't allow you to exit the system and go to the outside universe. So you're forever trapped inside.
Right.
Now, there are some fancy things, and when you get, maybe you learn this stuff on your own. There are lots of good, YouTube videos out there that describe general relativity for more of a lay person. And one of the things we notice is that, when you cross the so-called point of no return in a black hole called the event horizon, there is a shift in the way the coordinate system is set up, right? So for those of you who are familiar with coordinate systems, if you wanted to describe your location, let's say, Robert, there's a party at your house tonight.
Right.
By the way, you forgot to invite me, so make sure you rectify that.
I will fix that.
Oh, thank you. Appreciate it. And are we going to have pie for this? No, just kidding.
Absolutely. You can't get away from pie.
Now, Robert, he could be a mean person, and he's not. He's not this at all. He's totally opposite, okay? Diametrically opposite of this. He could say, I want you to come to my party. I will see you when you get there, and then walk away from me. And what's the questions I'm going to have? Number 1, when is the party?
Mm-hmm.
Number 2, where is the party?
And I say, I forgot all about the when, I will admit.
See, I need position information. I need some type of coordinate system so that you can tell me that I live maybe at this area in the city relative to the way the city streets are laid out. You can tell me, the nearest intersection of cities or whatever. There has to be some type of coordinate system, some reference that I know where to find your house, your location where the party is going to be at. And of course, I need the time information to go with that. In general relativity, what we discover is when you cross that event horizon, if you're the unlucky person that falls into a black hole, and by the way, never take that bet. If somebody offers you half of Ben Franklin to fall into a black hole and they say you'll get the other half in your return, don't take that bet. It's not worth the money, and you'll never get it, even though they may give you $1 billion, right, for doing this. So you cross the event horizon and the coordinate system changes in the sense that as you head towards the very center of the black hole, you're no longer traveling through space. Most of your traveling is through time. Remember, in general
Okay.
relativity, it's space plus time and space-time.
Right.
So in sci-fi movies, that allows us to say, the space-time continuum is disturbed because of the presence of an evil force from areas beyond, right? Well, what does that space-time continuum mean? It's not a made-up terminology.
Right.
It's the fact that we have to worry about space and time. They go together as a four-dimensional type of system. And when you cross that event horizon, you go forward in time. You can't prevent that from happening, but forward in time, that direction, quote unquote, then is towards the singularity. So from that point of view, you can't avoid the singularity once you cross the event horizon, unless you can stop going forward in time.
Okay.
That's
That
sort
makes-
of another
that makes
twist
sense.
of thinking about it, you
Right.
see. So if nothing can escape from a black hole, how do we know they even exist in our universe? What do you think, Robert, on that issue?
Well, I actually know a little bit about this because this was something I got interested in as a kid. And, how do we know they exist and what goes on? Well, the first one that we got direct evidence of was called, it orbits a star in the constellation of Cygnus, and it's called Cygnus X1. And what happened there is we saw this star in Cygnus that we could see, called the visible companion, and it was moving in an erratic fashion, but one that, I say erratic, it wasn't really erratic. It was moving in a way that we knew something was disturbing its orbit by being in a mutual orbit with it. And so when you see that's going on, you can sit there and use the spectra and the movement of the spectral lines, which we'll get onto that in another episode. And you can see how it's moving and make calculations to determine the mass of the companion. Well, this companion was extremely massive and couldn't be seen. It was more massive than a neutron star could be even. So that's evidence of a black hole. Indirect evidence, certainly, but you can't see the companion. It's got more mass than could possibly be there by under known laws of physics. Guess what it is? The next thing is you could theoretically see the accretion disk. If the black hole is feeding, there's this matter gets drawn into due to angular momentum into a disk around its equator, essentially. And as it falls in, of course, it gets compressed, plus it's moving against itself, so it heats up. And while we can't see the black hole, we can see light given off by that heated mass falling into it. And that's actually been done now, too. So
Robert, one of the interesting things is way back in the 1600s, early 1600s, very famous person. You might have heard of their last name, Kepler. Have you heard of that
Kepler,
name?
yeah, I like Kepler.
Yeah.
Kepler's great.
Well, one of the famous things that Kepler had done is that he had put forward what's called his 3 laws of planetary motion. So he took the observations that were amassed over time from Tycho Brahe and his collaborators, and he mathematically fit the orbit of the planets, in particular Mars, to the observations. And he discovered, among other things, that the planets orbit the sun on elliptical orbits, not on perfect circles, that Copernicus had envisioned several decades before before Kepler's laws were published. But the most interesting thing that's relevant to what we're talking about here is Kepler's 3rd law of planetary motion. And that 3rd law essentially states that if you know how long it takes, let's say, a body to orbit another body, so let's say a star to go around a black hole, for example, and you know how far apart those objects are on average, then you can calculate directly the sum of the masses of those 2 objects. Now, how does that help with Cygnus X1? Well, from spectroscopy, you can look at the normal star, the one that we can see in this system.
Right.
By analysis of its light, you can tell what type of star it is, and you can tell what its mass is. So let's just assume, for example, and I'm going to make up some numbers here to exaggerate. Let's say that from Kepler's 3rd law, we know that the sum of the masses is 1 million times the mass of our sun. Okay?
Ooh.
Okay? So we're going to go extreme here,
Okay.
just to put the point across. But from your analysis of the ordinary star in that system, remember it's an ordinary star that you can see because it gives off light, just like our sun gives off light. The other object in the system is a black hole, and it's not giving off light at all. There's nothing around it.
Okay.
It's just orbiting the normal star. If the combined mass from Kepler's third law is 1 million solar masses, and by analyzing the starlight of the ordinary star, we find out that it has a mass of about 20 solar masses. What do you think the mass is of the black hole, the unseen object?
Well, it has to be, let's see, what's 1 million minus 20?
Right. Right. So let's round it off. 1 million.
1 million.
Right?
Right.
Okay. Do
Which
you know
is
of any?
essentially what happens with the solar system, by the way.
Yeah. Do you know of any stars in the universe that have a mass of 1 million solar
Oh.
masses?
No, the heaviest one I know of is right around 100 solar mass.
So the question would be, what would have a mass of about 1 million times that of the sun, and yet it is confined in a relatively small region of space and doesn't emit light at all?
And I'm going to call that a black hole.
That's right. That's the only thing we know of, the only candidate that would fit in this case. So is that direct evidence of a black hole?
No.
No, it's indirect evidence, but it's very, very interesting.
It's convincing evidence.
Convincing. Now, there was other things that came along,
Mhm.
and those include something that we discovered with direct detection back in 2015, and this was the detection of gravitational waves.
Okay, right.
So gravitational waves are, if you like, these undulations, these fluctuations, well, I'll use the same terminology we used earlier, in the space-time continuum, for
Right.
lack of better words there. And that's a prediction from the general theory of relativity. So if the general theory of relativity as its present form, if it's valid, and as far as we can tell, we can think about how you can never prove a theory right. You can always prove a theory wrong if you have the right evidence or observations or experimental result. But from the general theory of relativity, a prediction would be that there should be these gravitational waves that get emitted from accelerating objects. Think of objects moving around, right? So think of, for example, the Earth going around the sun. The motion of the Earth generates gravitational waves. They should exist. They're fairly weak. In fact, the detection of this is a whole story which we can get into another time.
If you have an analogy, think of it as a boat moving through water. It gives off waves. It causes the medium, space-time in this case, to flex.
In fact, if you want to learn all about it, one of the suggestions I have, and this is the first time we're doing that, is actually a book by Govert Schillings, and it's called Ripples and Space-Time. So this was written about the discovery made in 2015 about the detection for the first time of gravitational waves. In fact, several people won the Nobel Prize in Physics with part of the system and the theoretical work that was done in the detection of gravitational waves. Now, because of the gravitational waves, we knew way back in the 1970s that there was a black hole orbiting a particular star known as a pulsar.
Aha.
This is an end state of a massive star that blew itself up at the end of its life. The central core of that star collapsed into a very high density object that we call a neutron star. And under the right conditions, the neutron star can emit beams of light, and those beams of light can sweep by the location of the Earth. And we detect it initially through radio observations, but since we put up a lot of instrumentation since its first discovery in 1967, we can detect pulses coming from these objects, both in optical and in gamma ray and other wavelengths as well. It's not just isolated to radio. That's just how they were initially detected. Now, with the release of gravitational waves from this particular binary system, this pulsar and black hole, what happens is that the time it takes for the system to make a complete orbit around each other, around their center of mass, as we would say, changes as energy, if you like, is being bled from the system, and that energy is coming out in the form of these gravitational waves. So what people have done is they've tracked the change in the orbital motion of this system very precisely, and it actually follows the prediction of what you would expect if gravitational waves are emitted. Okay,
Yep.
so we know gravitational waves exist. Okay, actually, that's a double pulsar system, right? That wasn't one with a black hole.
I think it was, yes.
It's the
I
double
think they've
pulsar
since
system.
found evidence of a few double black hole,
Yeah, for
neutron
sure.
star black hole systems.
Yeah, so that
But
was the initial indirect detection of gravitational waves, if I'm not mistaken. But from that time, the important point is that we can look at what would produce gravitational waves. And what we discovered is a lot of the candidates that we've observed, and certainly the first one that was discovered in 2015, was the so-called binary black holes. These
Right.
black holes that merge together, and in that merging process, they release a burst of these gravitational waves. And these gravitational waves then actually tell us what is the origin of those waves, what is the progenitor, what produced those waves. And in the cases that we've detected, we have tens and tens of candidates now that involve a black hole. If black holes don't exist, then we're not going to get the type of waves that we've observed
Right.
from these systems.
In other words, I'll make it clear. General relativity and our other theories make predictions that say we should detect these types of gravitational waves. And guess what we're detecting? Those types of gravitational waves. So, this is not baseless. This is not just somebody guessing, oh, this must be what it is. We are detecting exactly what we predicted we would detect. So, either the universe is very contrary and likes to giggle at us, or we're on the right track, folks.
And the other thing, talking about orbital motion and how that gives information about the mass of the system through Kepler's third law. If you watch stars that orbit the center of our galaxy, the Milky Way, what are the type of mass numbers that we get when we do that type of calculation? Do you recall?
I honestly don't. I really don't. Sorry.
So remember, there are several of these stars that are near the center of our galaxy,
Mm-hmm.
and people have been observing them for several decades now.
Right.
And the type of mass number they get, the combined mass of the star and the whatever object they're orbiting around with in partnership here, is on the order of about 4 million times the mass of our sun. 4 million. So when I used that example earlier of 1 million, that's where I was heading towards.
Okay.
Okay? So we see situations 4 times greater than that in terms of the total mass. So as far as we can tell, you don't care about the mass of the star because it's just several, right? You're talking about 4 million, right? So it's really negligible. In some sense, it's rounding off error, right? You can think of it that way, right?
It's something you can think of it, except it's even worse than this. But it's like a bug hitting your windshield when you're driving down the highway. The bug added mass to your car, but it's negligible compared to the mass of the car. So, this is a much worse case. This supermassive, as we call it, black hole is sitting there, and though they're stars, they're bugs on its windshield.
Yeah, I mean, it'd be like if I gave you $1,000.13, would you tell everybody I gave you $1,000.13, or would you just say, "Hey, he gave me $1,000"?
Right.
Right. So we have an object that's at the center of our galaxy that has a mass of about 4 million times the mass of our sun, and it doesn't emit light. So once again, the only possible explanation, the reasonable explanation we have, is it must be a black hole. Now we talk about masses that are millions times the mass of the sun, or even billions of times the mass of the sun. We call these supermassive black holes. That's the terminology that we use to distinguish those from black holes that only have a few tens, let's say, times the mass of our sun. They're more like stellar mass type of black holes. Now, when people discovered this, of course, the interesting thing you think of is, well, that's for our galaxy, but there's probably nothing special about the Milky Way. That's kind of something that it's like the Copernican principle, right? Where Copernicus reinvented from the time of Aristarchus the fact that the solar system, and at that time in the 1500s, would be the universe as a whole. That's all they knew that existed, what you see in the sky with your eye alone. This is before the invention of the telescope. What you see is the fact that our galaxy, our sun, there's nothing special about the location of the Earth. Of course, there's something special about the Earth. It's the only place that we know of so far in the universe that has life and supports life, where there's intelligent life. And talking about it, well, wait a minute, Robert.
Mm-hmm.
If you came from another planet and you visit the Earth,
Right.
and you look down upon the Earth, and you saw all the activities people were doing today, here in the year 2023, what are some of the activities you would notice? Things like what? Warring, killing, stealing. Would you conclude that was intelligent life? Well, that's an issue we can debate.
That's another
later,
issue.
right?
That's something to
Okay,
forget.
so intelligent life, let's say we'll define it as a spacefaring nation.
Okay.
Okay? So
We're getting there.
evolved the technology to the point where we can get outside of our atmosphere, go into space and visit whatever we want to do, send out robots, space probes, and so on. Okay, so we have that aspect of thing. Okay, but as far as we can tell, our galaxy is one of at least a trillion other galaxies in the observable universe. There's nothing special about ours. So if there's a supermassive black hole sitting in the center of the Milky Way, what about that galaxy next door? Would that have a black hole in its center?
I would lay favorable odds for it.
Well, we should look, right?
We should look.
We can guess, but we don't guess in science.
Absolutely not.
We believe something is true. It's not a belief system in that sense, right?
Right.
We want evidence. So we need to look to see if there are black holes in other galaxies. You can look, for example, in the nearest galaxy to our Milky Way that's similar to our own. You know which galaxy that is, Robert?
Which one is closest similar to our own? Isn't that Triangulum?
No.
Okay, that's
Terms of-
large, in other words.
Yeah, roughly same mass as ours.
And then that would be Andromeda.
Andromeda. So isn't that a Trivial Pursuit question? What is the furthest, most distant object you can see with just the unaided eye? And it's the Andromeda Galaxy. You can see that in a dark location.
Right.
It's about 2.5 million light years away. So what does that mean? Well, light travels a distance in 1 year of about 9.5 trillion kilometers, about 6 trillion miles. So, multiply that by 2.5 million. That's the distance to the Andromeda Galaxy. So it's pretty far, but it's really in our backyard on the scheme of the universe as a whole. It's really nearby. And so when we look in towards the center of the Andromeda Galaxy, we also see evidence for a black hole. In fact, most normal galaxies, as we would say, seem to have black holes at their center. Now, there is a particular galaxy known as M87. The M comes from a catalog named Charles Messier, put together this catalog several centuries ago. And the reason for that, what motivated him, he was interested in finding comets. And when he would scan the sky with his telescope, a lot of times you come across things which are not comet, but are comet-like in appearance, like nebula, right? Emission nebula, reflection nebula, supernova remnants, and so on. And with a relatively small telescope, sometimes it's hard to tell between the two. You have to kind of watch it and look for motion and so on to see if it's a comet or not.
Right.
So Charles Messier said, I'm going to put a catalog together, note where all these cloud-like things are in the sky, okay? And then when I stumble across that location, right away, if I think if it's a comet or not, I look at my catalog and say, no, I've already seen this before. It's not a comet. And so there is a particular galaxy that's in that catalog, M87. Now, M87 is kind of cool because when you look at one of the things we see poking out the side of M87 is a jet of material.
Right.
And as we've learned when we study these objects, we discovered that jet is coming from the environment outside the event horizon of a supermassive black hole. Now, wouldn't it be interesting? Because this black hole is about 6.5 billion times the mass of our sun. And the more massive a black hole, the larger is the event horizon, the greater its circumference.
Right.
Okay? So if you had the technology, okay, and you wanted to look at one of these black holes, at least look at the shadow, because remember, light doesn't get emitted from a black hole, right? In order for light or anything else to get away from a black hole, when you're within the event horizons, you have to travel faster than the speed of light. And as far as we know, that's, we can't do that. We don't see anything that can do that in nature in that sense. Now, it turns out that if you want to see something that's extremely tiny from our location here on Earth, like the black hole in the Milky Way would be, it'd be extremely tiny. We know, for example, if you have a friend that's 6 feet high exactly, okay, and if you walk a certain distance away from them, they look smaller and smaller in apparent size.
Right.
Okay, and if you double the distance, they look 1/2 the size. Okay, and that continues as you get, let's say, further and further away. Now, by the time we get far enough away from the center of our Milky Way to where we are here, okay, roughly about 26,000 light years from the center of the Milky Way, that black hole becomes so small in size, it becomes essentially invisible.
Right.
Okay? So what we have to do is to come up with some technique, some method, some strategy, which will allow us to see something that's extremely tiny that hasn't been seen before.
Mm-hmm.
And lo and behold, we've actually done this. This is known as the Event Horizon Telescope. Now, it turns out the black hole in M87, which is about 55 million light years away, roughly, given that it's much larger than the black hole that's in the center of our Milky Way, because it has a lot more mass, 6.5 billion times the mass of our sun, where ours, of course, is the 4 million times the mass of our sun, that they're almost relatively the same in apparent size. Even though the M87 black hole is much further away, it is much larger.
It is much larger.
Because
right.
of its larger mass. So they're, in terms of angular size, they're almost the same. So we've actually used the Event Horizon Telescope to look at both of these black holes. So Robert, if you want to pull up the slide that shows that.
There we go.
Okay, so what you're seeing here, so first of all, on the right is an image. This is taken at radio wavelengths. And of course, if you showed an image in black and white, people are disappointed. They're like, oh, the favorite program from back in the 50s is black and white. Well, I love to see that in color. So we're spoiled nowadays in some sense. We want to see everything in color. So because of that, the demand from the public, scientists color code these images. And what you're seeing here is an image taken at radio wavelengths of the vicinity of the black hole in the Milky Way. That's the frame on the right. Okay? And we're comparing that to the one on the left, which is in the vicinity of the black hole that's at the center of M87, which is a galaxy, roughly 55 million light years away, as I mentioned. Now notice the difference in masses. They're labeled here. So the one in M87, 6.5 billion times the mass of our sun, and the one in the center of our Milky Way, 4 million times the mass of our sun. So these are very, very excruciating type of observations that were made with the Event Horizon Telescope, which is a series of radio telescopes at different positions on the Earth, right? For example, in the South Pole, in Mexico, there are telescopes in the United States and in Europe, and they're adding more all the time. There's one in Greenland and so on. And the idea is if you can combine the signal from multiple telescopes spread over different locations on the Earth, you can use this very fancy technique called interferometry to combine the signal from those multiple telescopes. And it acts like, in terms of being able to see details, what in science we'd say that it's resolving ability, it acts as if you have one giant radio telescope that is the size of how far out these different telescopes are spaced.
Right.
So if you get enough of them on the surface of the Earth, it would be like if one side of the Earth faces towards a certain object, it's like the whole side of the Earth acts like one giant radio telescope from the point of view of resolution. That's important.
That's an important point, and
Yes.
maybe one we ought to cover someday,
Yeah.
but not today.
Right. But for this case, we're trying to resolve to see then what's at the center of the Milky Way and other galaxies as well. And clearly what you see here on this slide is that we have been able to do it. This is pushing the technology to the limit. Okay?
Yeah,
This is essentially the best that we can do right now.
Each of these image folks went into the petabytes of data going into the image, which, most of us are familiar with mega and gigabytes. Peta is another 1,000 or million times that.
Yeah, so you got to go to
Yeah.
terabytes.
Terabyte and then petabytes.
Yeah.
So it's 1,000,000 times a gigabyte. So this is 1,000,000 gigabytes worth of data went into each of these images. So they were calculating and running the numbers and feeding out all together to combine into one image for years. And that's just something I like pointing out too, is this is not a work of, they just sat down one night and combined it. No, this was years of work. So
Yeah, and the other thing, there's a lot into it. That you can read the story about the Event Horizon Telescope. There are several books, which I should have brought one along with me, that actually describes it from a layman's point of view, all of the thing that goes behind doing constructing some of these type of images. Now, the important thing to note here is when you look at these images, you see the different color spots. You're not seeing light coming from the black hole itself. In fact, the scientists call this the shadow of the black hole. That's that central darker area. It's in the center of each of these panels. Now, what you're seeing here is light that's emitted from gas that lies outside of the event horizon. If you're further away than the event horizon of a black hole, light can escape. You don't need to travel faster than the speed of light to get away from that environment. And so light is coming from gas that's been heated up in the vicinity of these black holes, and that's the sort of ringing effect that you see. Now, part of the thing that's happening here is that space is distorted near the black holes. Remember a definition of a black hole. It's when you can think of it as when space-time is curved in such an extent it curves in on itself. So if you're trapped in that boundary, you can't escape no matter which direction you travel. You're forever trapped. So near the vicinity of the black hole, space is highly warped. It's one way of thinking about it. It's almost like going to a state fair or amusement park and you look at all these different mirrors, right? And when you look on it now, you look like you're 20 feet high and you're 3 inches thick through the waist, or you look like you're 20 feet in length and in terms of your width, and look like you're 1 foot high. All these fun mirrors, right? And so that's kind of what's happening in the vicinity of the black hole. It's being distorted like this. So part of the ring that you're seeing here is actually light that's emitted from the far side of the black hole relative to us. And because of the distortion of the space, some of that photons actually reach us here on Earth. So that's the sort of ringing effect you're seeing here. But the point that I wanted to illustrate here is that you're not seeing light coming from the black hole directly. It's from outside that event horizon. The other thing to note is that the observation, the image that you see here, the image is, the one on the left for M87 was actually released before the one from the center of our Milky Way.
Right.
The reason for that, it turns out, at least the major reason, is that things are changing over a relatively short time scale near the black hole in the center of our Milky Way. So over the course of just hours and days, the gas itself is moving around. It's changing. And so when we're looking at an object like that using this interferometry techniques, it works best if things are stable and not changing, if things are static. That's more of the case for M87, and it made the processing a lot easier, it turns out. Right. But when things are very dynamic or changing on scales, significant changes in the motion of the gas and its visibility from Earth over the course of several hours, that becomes a real problem to fet that all out when you're analyzing the data taken from these multiple radio telescopes, as it turns out. So it took a little while to get the image for the black hole in the center of our galaxy.
Again, to try to put it in perspective, it's like trying to take a picture of I'll use something from my day. It's like trying to take an image of a John Smoltz fastball. He's throwing that ball at nearly 100 miles an hour, and if you just use your phone camera or something, it's just a streak because it's moving too fast. So you've got to sit there and use some technique to actually close and open that shutter and get a picture at a much faster, higher rate. And so that was part of the problem.
Yeah, definitely. So it took a lot of really sophisticated, detailed processing to finally get the image then of what we see in the vicinity of the black hole at the center of our Milky Way. But the point here, what motivated all of this discussion is now we have direct proof that number one, black holes exist.
Right.
Number two, there is one at the center of our galaxy. Number three, what happens in the very center of black holes at the singularity? That
We're back to that.
That's right. That problem never went away. We took this long route to get to the point where we can no longer dismiss and say we don't have to worry about what happens at the exact center of a black hole.
Because they don't exist.
Yeah.
Oops, they exist.
That's right. So now we have to go back and figure this out. We have a lot of work that needs to be done in trying to understand black holes.
Come join us. Win your Nobel Prize.
Exactly. Now, there's a lot of sophisticated sort of work that's being done on black hole science, way more than what we could even hope to get into in a podcast today, for example. But just rest assured that this is one of the most important questions in astrophysics today, is what happens at the center of a black hole. In fact, hopefully you can appreciate, if you've listened to all of this podcast up to this point, that whatever we find out, whatever new knowledge we gain, it's going to have ramifications for everything we see in physics, all the way from what we interpret, macroscopic objects, the general theory of relativity, all the way down to very tiny things, quantum mechanics.
Mm-hmm.
You know, in quantum mechanics, because you deal with things that have almost no mass at all, like an electron, for example, it's not like you say, oh, I better slack off on the number of electrons I eat today because I ate 5 more than I should have. I know I might tip that scale a little bit higher, you know. That doesn't happen. When you deal with electrons, when you deal with things at the subatomic level, you don't worry about its mass. It's negligible. If you don't worry about its mass, then you don't worry about gravity, right? So gravity is negligible for things that we do at the subatomic level in general, dealing with quantum mechanics. But Robert,
but especially when you get down to the nucleus, you've got a lot of mass in a small amount of space. You've got a small volume and a high mass comparatively. So gravity starts playing a role again.
well, remember that mass is the energy of motion of a lot of those things.
That even causes
and the potential energy.
That mass would exceed the rest mass.
That's something we should talk about in a future podcast, is where ultimately does the mass come from when we talk about particles.
That would be a good one, yeah.
And we'll find, you get this, when you learn it in high school, I assume, where you learn that, atoms have made up of particles like protons and neutrons in the center and orbiting around them on the outside. And it's the wrong
picture.
It's the wrong picture, but it's a very simple thing that most people can get, and then you build up the complexity, of course, later on. And is that electrons sort of orbit on the outside, like the planetary model of the solar system applied to the atom.
It's like I tried telling my high school students when I was teaching high school, and do still tell college students, knowledge is like a brick wall. You can't put the top brick on without the bricks below it. So sometimes we're not lying to you, we're just giving you an easy to image thought to describe these things that you can deal with right now. And then we add on some more knowledge and you can finally see the big picture, what's really going on.
Right.
And
if you go to university and you learn things, for example, you don't enter university, say right away you're going into graduate level quantum mechanics. And even though you haven't learned any of the fundamentals yet.
Right.
I mean, that's just too large of a chasm to
Take
cross.
math, folks. Takes lots of math.
Right. You just have to study, right? Don't worry about the math. Sometimes when we get hit with calculus, it seems like, what did I get myself into? And really, it's just a matter of focusing.
Right.
Right. Just
I will agree.
focus, and then it'll come a lot clearer, and you can do it. And of course, seek help. Talk to your professors, talk to your teachers, talk to other students who may get it before you do.
Talk to your friendly neighborhood lab coordinator.
Yeah. You can even consult, things on Google. There's lots of lectures I notice nowadays on YouTube and other places which try to describe calculus, at a level that most people can get if they really concentrate.
Right.
And that's a good thing, right? All types of references and information can only help.
Absolutely.
So we know black holes exist, and that may change the way we think about things going into the future, because we need to solve it, whether that involves quantum gravity, as I mentioned before. Some people work on things you might have heard of called string theory, and we're always looking for, make a prediction. So when we talk about theories versus hypothesis now in science, Robert, do you have some words you like to say about that?
Yeah, this is one that I often get up on a soapbox about, because in common parlance, a theory is a guess. It's I have a theory about that. Okay, in science, that is not the case. So I called up and got a few points. So dictionary.com gives us this definition of a scientific theory. And it's a coherent group of propositions formulated to explain a group of facts or phenomena in the natural world, and repeatedly confirmed through experiment or observation. So, and then Wikipedia gives us this explanation that it basically boils down to the same thing. And I see I cut off part of both, so I'm sorry about that. But the end result is that people say, it's just a theory, so it's not backed up by anything. It's just somebody says this is the way it is. Well, that's not how scientific theories work. They are backed up by observation or experiment, or predictions have been made by the theory that have then been tested through observation or experiment. So anytime someone is speaking on a subject of science and says, well, it's only a theory, you know immediately, as soon as those words come out of their mouth, they don't know the science. Okay? Because if they did, they would know that a theory is not some kind of guess. It's not some kind of, I think it's this way. It's a matter of, hey, this has been made predictions that have been borne out. This has been shown to be true, not proven. The only science that proves anything is math. Okay? But it shows, it demonstrates that this is the way things are. So I'll get off my soapbox and let you get a word in edgewise.
Well, the thing that I mentioned prior when we talking about theories is, for example, you can never prove a theory correct.
Right.
But you could potentially prove a theory wrong.
Right.
Now, that works in the sense you have some theory, let's say the general theory of relativity. And in the general theory of relativity, one of the predictions, as we mentioned today, is the fact that there should be these undulations in space-times, these gravitational waves should exist. Okay. So we develop instrumentation that's sense enough to detect gravitational wave. And by the way, if the average gravitational wave, when it washes by the location of the Earth, it can stretch and squeeze space about 1/10,000th the radius of a proton.
Wow.
It's so minute.
We're going to have to talk someday on how they
We'll get into
measure
that
something
someday.
like
That'd take a whole podcast
Absolutely.
to explain that. But that's why we never, you don't look at the weather forecast and say, oh, be careful today, there's a chance of a strong gravitational wave might be passing through, right? So we don't have to worry about any of that because most things in the universe, where they're located, the gravitational waves are negligible. Now, if there's something that's really nearby us, that's a different story, and we also can save that for another day. But if we looked, and we have built sensitive enough equipment, that given the theory, we should have detected gravitational waves, and yet we don't see any. That theory is wrong from the point of view that it either needs to be modified or it needs to be thrown in the garbage can.
In the garbage can.
So just that one observation, that we took all of this advanced equipment that we've developed over time, we looked for gravitational waves, they weren't there. That's the downfall of the general theory of relativity as it was prescribed by Einstein.
Because I was about to point out that if we hadn't found gravitational waves, it would have been a matter of, general relativity needs to be modified. It would not have been thrown out. Why? Because every day you use your GPS proves general relativity. So there's a lot of evidence that says, no, general relativity is right. But if it got that one thing wrong, we now have to modify it. We now have to say, okay, what caused that to be wrong? What in this do we not understand yet?
Yeah, so from that point of view, it only took one thing to cause us to rethink everything.
Right.
But let's say we find gravitational waves, which we did. We detected them 2015. It's been 7 years, 8 years almost now. Okay. Does that mean that general relativity is perfect? We'll never have to do anything to it?
I hope not.
Well, the answer is,
No.
well, we don't know, right?
We don't know.
Because you could do another experiment, you could do another sort of observation. All of the results are totally consistent with the general theory of relativity. But you could do, for example, 1,000 experiments or make 1,000 observations, and it was that 1,001 experiment or that 1,001 observation that was inconsistent with the theory. That's all it takes.
Now, I will say this. You better be able to repeat that inconsistency.
Right.
Because it might just be what we call now I forget the term, an outlier. In other words, there's enough random scatter and enough things go wrong with equipment that every now and then some outlier, something outside the scope of what you expect happens. You don't trust one, you get several.
Yeah, and the thing to note here is, Newton gave us a modern form, if you like, of the understanding of gravity in the late 1600s. Einstein comes along in about 1915 to give us an even more modern form of gravity. But it's not like Newton is totally wrong, throw everything in the garbage. No, we only need Newton's laws, Newtonian mechanics, to send spacecraft to Pluto, for example. We don't need general relativity. So it's just that Newton's law of gravity is a great approximation, but Einstein's is closer to reality.
Is better.
It incorporates more, it explains various things in our solar system, like the orbit of Mercury, for example, was not precisely known if you just used Newton's laws. In fact, people speculated there was another planet in our solar system, but there isn't. That was closer to the sun than Mercury than Mercury, I should say. It turned out that general relativity is a better explanation of gravity, and with general relativity, it doesn't need another planet closer to our sun than Mercury is to explain totally the orbit of Mercury itself.
Right.
Okay, Robert, I think this is a good time to wrap up.
Right.
So please come and watch us then on next Tuesday at 3 p.m. Central Time. We'll do this again. And remember that one of the things we like to end is with a quote, and I'll use the same quote as I used last time.
Oh,
Do
okay.
you remember that quote, Robert? Would you like to say it?
I don't remember that quote.
That is the
Sorry.
beginning of wisdom is not to know all the answers, but to realize the questions to ask. Thank you very much, and thanks for listening.
Thank you, folks. You have a great day.